Our next assignment, assignment 23, comes from section 6.1. We're going to review using properties of exponents. Your essential question is, how do you use properties of exponents to simplify expressions? And I'm going to start us off on, there's a page in our book, page 323, that references these properties and actually gives you names of these properties. I'm not going to name the properties, but you are responsible for knowing these properties. Not the names of them, but definitely of knowing these properties. So, properties of exponents. Let's see if I can get a better view here. Page 323. So, I'm going to go through each and every single one of these and give you an example of each one. I'm not going to necessarily name it though, but each one does have a name. So, product of powers properties, power of a power property, and so on. Okay? Okay, so starting with our first property, you basically have like bases. So two numbers like bases, like A and A, being multiplied together, and they have different exponents. So basically what you're doing here is you're multiplying like bases with exponents. And when you multiply like bases and they have different exponents, or even the same exponent, you basically add those exponents together. So this would be the same as A to the m plus n. Okay, and then I'll do one actually underneath each one of these. So, for example, if you have x to the 5th times x to the 3rd, that's going to give you x to the 8th power. Because you just add them. So when you're multiplying like bases with exponents, you just add those exponents. Okay, next property is when you have a base that's raised to a power, and then you raise that entire thing to another power. Okay, this means that you're going to take whatever the power was that your base was originally being raised to, and you're going to multiply it by this power outside the parentheses. So this would simplify to A times, or to the mn, or m times n. So for example, if I have x to the 5th, and I raise it to the 3rd power, this gives me x to the 15th power. Okay, so you have a power being raised to another power, which means you multiply the powers. Let's see, let me get a highlighter. We'll start highlighting the different properties. So this one you are definitely responsible for. You've been using it probably for quite some time. Okay, and then this one, power raised to another power. All right, next one. This is where you have a product raised to a power. So you would have, for example, A times B to the m power. Well, this power outside the parentheses is going to be given to each base, or each, I should say, factor of the base. So it's going to be given to the A. So you'd have A to the m power times B to the m power. And so an example of that, maybe I have 3 times 5 squared. I don't like that example. Maybe I have 3 times x squared. Well, this basically means that I'm going to have each factor of this base is going to be raised to the 2nd power. So I'm going to have 3 squared times x squared. Or in other words, I'm going to have 9x squared. Okay, next property has to do with negative exponents. So if I have a raised to the negative m, well, a negative exponent, really we don't work with negative exponents. In order to deal with a negative exponent, what you do is you basically take the reciprocal. Okay, so a is really a over 1, the reciprocal of a over 1 is 1 over a. So this is really 1 over a to the m. So let me give you an example here. What if I give you 1 over 4 to the negative 2? Okay, well, really, to get rid of that negative 2, I need to take the reciprocal of my base. So right now my base is 1/4, and the reciprocal of that will be 4 over 1, or just 4. Okay, and this will be 4 squared. So really I end up with 16. So here's the property in dealing with a negative exponent. And our examples below it. Okay, here's one of my favorite ones. Anything raised to the 0 power. It doesn't matter what it is. Anything raised to the 0 power is always going to be 1. Okay, that's all I can say about that. You take a flower and you raise it to the 0 power, it's going to be 1. Okay, so for example, if I had 5 to the 0 power, that's going to be 1. Okay, so you really have to get your brain out of the fact that anything to the 0 or anything times 0 is 0. This is not timesing by 0. This is saying 5 to the 0 power, and that's going to equal 1. Okay, same thing with these negatives. A lot of times when we deal with negatives, all of a sudden we think we need to actually make our numbers negative. That's not the fact. Okay, when you're dealing with any base raised to a negative power, then what you want to do is you just want to take the reciprocal of it, okay, in order to give it a positive power. So you have a to the m power over a to the n power. Okay, well, again, now we have the exact same bases, each being raised to powers, okay, and we're dividing. So when we did that with multiplication, right, like bases, and then we were multiplying, what we did was we added the two exponents, or the two powers, okay? So now we're dealing with division. So instead of adding those two powers, we're now going to subtract them. So this would really be a to the m minus n. So an example of that might be x to the 5th over x to the 3rd. So really this would be x to the 5 minus 3, or x squared. One more property. And this property has to do with raising a quotient to a power. Okay, well, when you raise, for example, a product to a power, notice that that power was given to each factor of the product. The same thing holds true with a quotient. When you raise a quotient to a power, each piece of that quotient, numerator and denominator, end up getting that power. So this is really a to the m over b to the m. Okay, an example of that might be 7. So I'm just going to do the example, let's see over here because I'm out of room. So I'll do 7 over 8 squared. So really this just becomes 7 squared over 8 squared, or 49 over 64. Let's work a couple of examples from your book. So I'm on page 326 now. And this is where I'm going to get your examples from. Okay, so why don't we start with number 6. This is, you have 3 over 2 to the negative 2. times 1 over 2 squared. And the directions here are to evaluate because we can actually come up with a numerical answer here. All right, well, starting out, I see I have a 3 on the numerator, but I have 2 to the negative 2 in the denominator. So I could break this up, right? Because I don't see that this entire quotient or this entire fraction is raised to the negative 2 power. Really, only the 2 in the bottom is being raised to that negative 2. Okay? So that doesn't mean I'm going to take the reciprocal of 3 halves. I'm only going to take the reciprocal of this bottom number here. So let me rewrite that for you. So this could really be considered 3 times 1 half, right? That 2 is really just a 1 over 2. Okay, so that 1 half is what's being raised to the negative 2 power. Okay, and then you still have 1 half squared. And from here, you can go a couple of different ways. I'm going to go ahead and use the fact that this is a negative and take the reciprocal of this. So we're really going to have 3. The reciprocal of 1 half is 2. Positive 2, because I took the reciprocal. And then this is a quotient being raised to a power, so both the numerator and denominator get squared. So this would be 1 squared over 2 squared. So this becomes 3 times 4 times, it looks like 1 over 4. And because this is all multiplication, I see common factors in numerator and denominator, so those reduce to 1s. And I'm just left with 3. Okay, why don't we do, how about number 12? Now the directions are to simplify because you have an x in there, so you can't quite evaluate. You're going to have 2 over x minus 3, everything raised to the 6th power. So this is the fact that I have a quotient being raised to the 6th power, so each of the pieces in the quotient, the numerator and denominator, are going to be raised to the 6th power. So I would rewrite this as 2 to the 6th power over x to the negative 3 to the 6th power. Okay, from there, well, 2 to the 6th power. Let's see, 2 to the 5th power is 32. So that might be something that you want to memorize. And then I need to multiply that by 1 more 2. So that 2 to the 6th power is 64. Okay, so on top I've got 64. And on the bottom I've got x to the negative 18. Well, again, you need to remember this whole thing's not being raised to the negative. Okay, only the denominator is. So really I can think of this as 64 times 1 over x to the negative 18. Or the whole thing 1 over x to this negative 18 power. So now I'm really just flipping 1 over x. So this becomes 64 times x to the 18th power. Let's see, let me circle my answers. All right, let's do another one. How about we do 46? That'll be my last one. Why don't I just go over here? Last one of these type. So 46, we have y to the 10th over 2x cubed times 20 times x to the 14th over x, y to the 6th. All right, so the first thing I'm going to do is I'm going to look for common factors in the numerator and denominators. So for example, I see that in my coefficients 2 and 20 have a common factor, right? They have a common factor of 2. So I can reduce this by a factor of 2, divide that out and get 1. Reduce this by a factor of 2, divide that out and get 10. Okay, let me rewrite it now. So I've got y to the 10th power over x to the 3rd power. And then I've got an I've got 10 x to the 14th over x, y to the 6th. And again, several ways that we can go about doing this. For me, I like to simplify before I multiply across. And that can get a little bit confusing sometimes. But the other way that you can do this is you can actually multiply straight across and get one number. So why don't I look at this both ways for you, okay? So the one way gets a little bit messy. Like the way that I would look at this, I would say I've got x to the 14th here, and I've got an x cubed here, okay? So this x goes away. I'm subtracting, right? I'm going to be left with 11. But then I've also got an x to the first power here, and I'm going to subtract that. No more x's in the denominator, and I'm just left with x to the 10th power. Okay? Same thing goes with, I see that I have a y in the numerator, okay, and a y in the denominator. Okay, so like bases, I'm going to subtract the exponent. So these y's go away, and this y I'm left with 4. So it looks to me like I am left with y to the 4th. I've got a 10 in there. I'm going to bring that 10 coefficient out to the front, and x to the 10th power. Okay, so that's one way of doing this. Okay, so let's go back and do this one more way. So let's say I still had my y to the 10th over x to the 3rd times 10x to the 14th, xy to the 6th. Okay, another way of doing this is to say, well, I'm multiplying whatever's on top together. So this gives me 10 x to the 14th, y to the 10th. You usually want to list your variables in in alphabetical order. So that's why I put x first and then y. And you usually want to have your coefficient out front. Okay, and then on the bottom, notice I have two like bases. So I add those exponents. This is really x to the 4th, y to the 6th. Okay, now from here, I can simplify. Okay, so I see that I have x to the 14th and x to the 4th. Well, I subtract. So I have no more on the bottom. I just have x to the 10th here. And y to the 10th and y to the 6th. Again, subtract. So you're just going to be left with y to the 4th on top. Which brings you right back to what I just had, right? You have 10 x to the 10th, y to the 4th. Okay, and that's how I should have written this. This was my fault. So this would be 10 x to the 10th, y to the 4th. That would be our final answer, no matter which way you get to it. Okay, and I'm sure that there's more ways. There's lots of ways to approach these problems. Okay, now I'm going to do a couple of examples from page 327. So this is page 327, examples. So I'm going to start with number 50. And you are given the fact that the volume of this cylinder is pi r squared times height. Right, so let's go to this one. So this picture right here. So, right, the volume of any cylinder is going to always be the area of the base, which the base here is pi r squared because it's a circle, right? So the area of the base, pi r squared, times the height. Okay, because we're just basically thinking of filling up this space with all of these areas of those base circles. Okay, so my radius is 2x and my height is x. Okay, and I'm going to come up with an expression for this. So again, my radius is 2x. My height is x. So I plug it in. So my volume now is pi. Well, my radius is 2x. So that's going to be 2x squared times my height, which is another x. Okay, so my coefficient now is that 2 squared. Okay, so I need to think about getting that, whatever my coefficient is, out to the front. Okay, so I've got a pi, which is approximately 3.14. I'm going to leave it in terms of pi. And then this 2 squared, right? Because I've got this product, and that 2 goes to both pieces of that product, or both factors. So let me keep the pi. This becomes a 4, an x squared, and then I've got one more x I need to multiply by. Okay, so I'm going to move my 4 out to the front. My 4 pi is my coefficient. X squared times x, that gives you x cubed. Okay, that was number 50. All right, and then I'm going to do one more with you guys. I'm going to do number 54. So 54 talks about its biology connection. You have a red blood cell, and a red blood cell has a diameter of approximately 0.00075 centimeters. Suppose one of the arteries in your body has a diameter of 0.0456 centimeters. How many red blood cells could fit across the artery? Okay, so we're asking how many of these can we fit in that length? Okay, so the diameter of this is smaller than this, so we should be able to fit several of these into there. The first thing I'm going to do is I'm going to write those in scientific notation. Okay, so I know it's maybe been a while since you've used scientific notation. Let's remember that a number this small is going to be multiplied by 10 to some negative power. So our goal is to get our decimal in between the first actual number. Okay, so in between 7 and 5. Okay, and I'm going to get my decimal, sorry, on this one, I'm going to have to move it 1, 2, 3, 4 spaces. So if I move it 4 spaces, that means I'm multiplying it by 10 to the negative 4. All right, so let's do that real quick. So starting with 0.00075, well, that is the same thing as 7.5 times 10 to the, again, I move it 1, 2, 3, 4. 10 to the negative 4th. Well, and why does that work? Okay, that works because this is really 7.5 times 1 over 10 to the 4th power, right? To get rid of that negative. So that really means that I'm basically dividing by 10,000, which would give me this really small number. Okay? So this is the scientific notation way of writing it. All right, and then the diameter of the actual artery, well, that's 0.0456. So if I move my decimal now to the right 2 places, right, I want 4 to be my first number. Okay, so this is going to be 4.56 times 10 to the, again, this is a very small number. And when I go back to this from 4.56, I want to be dividing. Right, so that means I'm going to have this negative exponent of 2, because I would move my decimal 2 places to the right. Okay, so I'm wondering how many of these can I fit into here? So that means I'm going to take this bigger number and divide it by the smaller number and see how many times it'll go in. So I'm going to take 4.56 times, and I think instead of writing an x, I'm going to say times 10 to the negative 4th over 7.5 times 10 to the, oh, I wrote that wrong. Let's try that one more time. So I'm going to take 4.56 times 10 to the negative 2, and I'm going to divide that by 7.5 times 10 to the negative 4. Well, notice here I have like bases, right? So this can be simplified. So this is really negative 2 minus a negative 4. Okay, so let's see. So I'm going to leave these two numbers the same, 4.56 divided by 7.5 times, okay, so 10 to the negative 2 minus a negative 4. So 10 to the -2 minus a -4. So what really happens here? These actually become positives. Okay, and I'm left with, let's see, 4.56 over 7.5 times, and it's going to be 10 squared. All right, well, 10 squared is really 100. So 4.56, whatever that, 4.56 divided by 7.5. Let's see, let me get my calculator. .608 times 100, multiplying by 2 zeros, so that means I basically move my decimal 2 places over, right? So this is really going to be about 60.8, or why don't we round down so that we can say, well, approximately 60, and I think it was red blood cells. So approximately 60 red blood cells will fit the diameter of that artery.